Good, good morning, everyone. Respected organizers, session chair, dear researchers and academicians. I am engineer Aditya Singh, ISTS. I've been an independent researcher, editorial review board member in 6 American international journals, IJSM, SSMET, IJESGT, IJSTS, IJRLEDM, IJSST, IJPAE, reviewer in 10 American, 5 Singaporean, and 1 Indonesian-based international journals, as well as also research mentor at Academy Nova World, Kalipur, India, alumni mentor registered by Amrita University Alumni, Amrita Vishwavidyapeetham, India, and ex-alumni mentor, LPU. Today's topic for the presentation is an optimization-led design framework and global case studies for post-disaster recovery shelters. Outline for this presentation, which will include introduction, literature review and research gaps, methodology, results and discussion, conclusion. Introduction, general. Disasters do not end when the ground stops shaking or the floodwaters recede. For millions of affected people, the post-disaster shelter phase determines survival, dignity, health outcomes, and long-term recovery. Despite decades of humanitarian response, post-disaster shelters still struggle with slow deployment, poor durability, lack of cultural sustainability, and unsustainable material use. This study evaluates global post-disaster shelter case studies and proposes an optimization-led design framework that integrates humanitarian needs with engineering performance and digital technologies. So, the engineering plus humanitarian systems, not architecture alone, is important. The core design challenges in post-disaster shelters are they must simultaneously satisfy the speed of deployment, structural safety, material efficiency, environmental sustainability, cultural and social suitability, and cost constraints. These objectives often conflict with each other. Faster shelters are usually weaker, and durable shelters are slow and more expensive. Local materials may reduce cost, but they limit scalability. So, this is not a single objective design problem, but a multi-objective optimization problem. Literature review and research gaps. Roughly 45 publications were searched, and recently published ones were further taken into account. And it could be said that uh, the studies in the current literature, they were having this most shelter studies focused on single disasters and limited integration of AI and optimization. Plus, there was a lack of life cycle performance evaluation and insufficient quantitative comparison across regions. So, of course, the descriptive documentation of individual disaster shelter projects are present, and qualitative assessments of humanitarian shelter failures, plus architectural typologies of temporal versus transitional housing are present. But there's an absence of optimization-led design frameworks, which is missing about the multi-objective optimization models which could balance speed, cost, durability, material efficiency, and cultural sustainability. If optimization were mainstream, shelters would algorithmically compared across scenarios, which the current literature rarely does. Similarly, there's fragmented analysis across disasters. So the cross-hazard, cross-geography synthesis, comparative lessons transferable between disaster types are absent. Then limited integration of digital uh, and artificial intelligence technologies. Even though they mentioned the current studies mentioned digital construction superficially and focuses on BIM for permanent buildings, but rarely applies artificial intelligence to humanitarian shelter design. So the use of AI-based decision support, digital fabrication logic, additive manufacturing for shelters, and data-driven deployment optimization are absent. Then overemphasis on speed or cost alone is another gap. And the relevance of this study, uh, the framing of post-disaster shelters as a multi-objective optimization problem, not a single objective optimization problem. So this is a theoretical contribution of this study, and it matters because it aligns humanitarian shelter designs with modern engineering methods and enables systematic comparison instead of ad hoc decisions. Then the cross-regional, cross-hazard comparative synthesis is done in this study, which compare Nepal earthquake, Turkey and Syria earthquake plus cold climate, and Haiti community-led recovery, and Philippines cyclone resilience. So they extract transferable design principles and breaks disaster type silos. And further, this study is relevant because of the linking case studies to optimization variables. Methodology. This study considered the publications and from the year 2020 to 2025 on post-disaster recovery shelters in the context of optimization-led design framework. The case studies were considered Turkey and Syria, Nepal, Haiti, and Philippines. And further, the optimization-led framework and utility were introduced. Global case studies, modular shelters 2015 Nepal earthquake, prefabricated housing 2023 Turkey and Syria earthquakes, community-led housing 2010 Haiti earthquake, and typhoon resilient shelters Philippines are covered in the next slides. Now, modular shelters are 2015 Nepal earthquake. This could be seen on the figure left hand side. The source is Architectural Digest. So the context of this modular shelters, it could be seen the massive housing loss in mountainous terrain after the earthquake and logistic constraints because of the terrain conditions and the climate variability was present. So the design approach was modular, lightweight units, timber, corrugated metal, and local stone were used, and incremental upgrading possible in those shelters. So, of course, the rapid deployment was present, local participation was present, but limited thermal performance and short design life were the major drawbacks. So, modularity improves speed, but optimization is required to balance durability and material use. Now, second case study, prefabricated housing 2023, Turkey and Syria earthquakes. This could be seen on the figure left-hand side. The context is the large-scale urban destruction happened during the earthquake in 2023, and there were cold climate conditions in these places, and there was government-led response. The design approach included factory-built prefabricated units, which could be seen in the figure, and steel frames, sandwich panels, and rapid mass deployment, which is visible in the figure. So, evaluation of these housing, it could be observed that the structural safety was present, thermal comfort was provided, scalability was present, but the cost was high and limited cultural flexibility were the drawbacks. So, industrialized solutions work at a scale but require cost and cultural optimization. Then, community-led housing 2010 Hati earthquake. This could be seen on the figure left-hand side. UNOPS, Claude Andre Nedon is the source, and the context was weak institutional capacity, informal settlements, and high social vulnerability uh, were there during the earthquake. So the design approach after the earthquake was owner-driven reconstruction. Local materials and labor were provided, and NGO technical support was provided uh, to recover from the earthquake at Hati. So evaluation of such housing, the cultural acceptance was present, livelihood integration was present, but quality inconsistency and limited structural reliability were the drawbacks of these housing. So social optimization is as important as structural optimization. Then typhoon resilient shelters in Philippines. This could be seen in the figure on left hand side, sourced by International Committee of the Red Cross, ICRC. The context, recurrent typhoons were present in Philippines, and coastal exposure because of such typhoons, and need for repeated designs. So the design approach used was elevated shelters, aerodynamic roofs, and reinforced lightweight frames, which could be seen in the figure. So evaluation of such typhoon resilient shelters included uh, could be found that they were disaster specific resilient and reusable. Reusability was also considered. They were cost effective, but the limited adaptability to other hazards was a major drawback. So hazard specific optimization improves performance but reduces general reliability. Optimization led design framework about and need. Based on these case studies, post disaster uh, design shelter design should move from rule based design to optimization led design frameworks. Core optimization objectives: minimize deployment time, minimize material consumption, minimize cost, maximize structural safety, maximize acceptability, and maximize social acceptance. Now, the digital role in this context could be seen that AI assisted material selection could be achieved, then multi criteria decision algorithms could be made, digital fabrication and prefabrications could be done, and additive manufacturing for rapid components could be performed so that the relief system could be done at a high speed. Then data-driven hazard response planning could be done through digital role. So optimization does not replace humanitarian judgment. It supports faster and better decisions under uncertainty. So digital twins, for example, for shelter systems could be used, AI-based deployment logistics, modular designs adaptable to multiple hazards, performance-based shelter standards could be considered in future. Uh, Results and discussion in figure 5, global temporary shelter growth could be seen, and in year 2024, the market value was 40 billion US dollar, but by 2027, it is expected to reach 52.74 billion US dollar. So, in the span of 3 years, it is expected to rise by roughly uh, 12 billion US dollars, which is a significant rise. So it could be said that in the coming years, the temporary shelter will be more in demand because of the disasters. So, of course, it will be a better option to use digital tools and focus on optimizations so that they could be made while considering all the requirements needed for people. Then figure 6 shows the growth of natural disaster management market, and in the year 2024, the market value was observed as 63.95 billion US dollar, but by 2029 it is expected to reach 114 billion US dollars. So it could be said that the market growth of natural disaster management is expected to increase by roughly 1.9 times in the span of 5 years. So, of course, the natural disaster management will be in high demand in the coming years. So, it will be a wise decision to incorporate digital technologies as well. Then figure 7 shows the growth of artificial intelligence in disaster risk management worldwide. And in the year 2023, it shows the market value as 479.5 billion US dollars. But by year 2031, it is expected to reach 2.15 trillion US dollars. So it could be said that AI use in disaster risk market will be significantly in high demand because increases almost 5 times in the span of just 8 years. So if we could incorporate all of them together, then the post-disaster shelters will be uh, made perfectly for the locals, and the recovery rate will be higher. Conclusion: the post-disaster recovery shelters and disaster significance were covered in this study, and optimization-led design framework, uh, why it is necessary and how it could be introduced, and current gaps in the literature and relevance of this study were uh, talked about, and global case studies were considered, which included Hathi, the Caribbean nation earthquakes, Syria and Turkey earthquakes, Nepal earthquakes, and Philippines typhoon conditions. And future market and scope were covered through the assistance of graphical analysis. These are the key references. Thank you.